Right, so I've been looking at this topic for quite a long time, and this is the first year I've introduced it. And what it's going to do is show you an alternative to the state diagrams that we've been using since the first year. And there are a number of reasons why I'm doing this when you look ahead and see what I'm going to cover next in particular. So if we have a look at this next slide. So ASM charts, arithmetic state machines. Okay, they look a little bit like flowcharts, as you'll see. They're not. There's no microprocessor, of course. So they are, one could argue, an alternative to the standard finite state machine diagram. You may have noticed with finite state machine diagrams they get very wiry and very messy quickly. So they're quite hard to follow, they get very cluttered, they don't scale. Now, we're going to use ASM charts which scale more gracefully. In other words, as the problem gets bigger, they seem to cope more. They're easier to read and understand, and they work just as well for the two types of state machine, Morton and Mealy. The Wikipedia article, which I mentioned there, is mercifully short. There is another reference I forgot to put on the slide, actually. It's funny because I've been looking at it all day. There's a book in the library by a guy called Zwolinski, and it's excellent, but it's a bit expensive to recommend students to buy it. Okay, so that's kind of what they're about. These are the symbols that they use. Okay, I'm going to explain each of these in turn because it does take explanation. There are a couple points where I can see people are going to get confused, and I know this because it wasn't that long ago, a couple of years, that I started reading this stuff, and I was confused when I read it until I reread it and reread it. Okay, and there was no one to explain it to me. So let's start with the state box. So a bit like the circle on the state diagram, and there's a convention that we follow. So the rectangle there represents the state, and as you know, a state, an internal state inside a machine, is only updated on a clock edge. Okay, so we don't suddenly leap states unless there is a rising or falling edge of a clock, depending how you're doing it. All right, the name of the state is written in the top left-hand corner. Sometimes they put a circle around it. I don't tend to bother. The book I'm going to recommend they do. Okay, the output is written inside. So for a Moore machine, output signal. Now that, when you just write the name of a signal, an output signal, you're assuming by implication that you're setting that to a 1, as I'll explain again in a minute. All right. If you write nothing, you assume it's set to 0. So that's a Moore output. In the right-hand corner, you might put a state assignment. So if you're putting numbers to states now so that you can build next state logic and do all those sorts of things and try and do state minimization, then you might write a binary number there. All right, again, I'm going to show you that in a minute. All right, so output signal, all right, which is a function of state, is written in the box. If nothing's written there, the output will be 0. If you write the signal there, it's a 1. All right, state name top left-hand corner, which at design stage is what you tend to use, and the state assignment, which you might write on a bit later on in the right-hand corner. And working those out so you get the simplest design is a whole subject in itself. All right, so let's just remind ourselves a few things about a state in a state machine. Okay, we only change on clock edges. They last the whole clock cycle, so you're in a state for a whole clock cycle. So any signal assertions you make, like output signal there, will be set for a whole clock cycle. All right, so I think when you see the examples, this will make a bit more sense. All right, so these are Moore outputs. So here's an example. This state is called connected. I could have called it anything, but I've called it connected. It's actually 0101 in binary, so we've got up to 15 states, up to 16 states here. Okay, so that's 4 D-type flip-flops. And I'm saying explicitly in one case that y equals 0, although I don't technically have to, because if I don't write it, we assume it is. And I've written a z, and that means z equals 1. Now I could write z equals 1 as well, but very often you don't, right? So you get used to it. When a variable's written, you assume it's a 1. All right, and all others of your outputs are 0. So that makes it kind of concise. There's less clutter. So in other words, you only write things on when you want to set them high. Generally, that's kind of how it works. You could always write, Z bar for active low signals. Okay, so that's one of the sort of by implication things. So far, nothing particularly different from the regular state machines. The other notation you see, all that's changed here is the label, where it's written in a circle. Okay, in the top, but it's always in the top left-hand corner. So this is another example. It's called state D. It's encoded as binary 3. Right. It's setting the output y equal to 1, and any other outputs we assume are 0. All right. Okay, no questions so far. I assume the audio is okay because no one is saying anything to the contrary. Okay, now decision boxes, state transitions and Mealy outputs. Let's start with state transitions really, which is what this one is showing. Now, a condition box, in the case of a state transition, is saying what is the next state. All right. So if we look at this one, we're in state A, that's the box at the top. Then we're testing some condition. It's usually inputs, signal inputs. Okay, and if that input is a 1, the next state will be C. And if that input is a 0, for example, then the next state will be B. All right. Now, the conditional bit is part of state A. You see that in the VHDL much more easily. Okay, so within a particular state, we usually do an if or a switch or something like that. So these are like the outgoing state transitions on the regular state diagram. Okay, so that's why I've put that dotted box around there. What else do we say about this? Yeah, so we say that conditional expression is associated with state A. It's all part of the same thing, right? Don't think it's separate. It's not. All right. They always have a state coming in before them or another conditional expression, as you'll see. But what follows one is either another. Actually, there's an error on that on the left. Must follow is associated with the state or and another conditional expression. So we can have multiple tests of different variables. I'll show you in a minute. I might just tweak this slide later before I upload it. Okay, so in this one, we're in it, as I said, we're in A and we're setting some output maybe. And then if the input, whatever it is a 1, the next state will be a C, and you might get a different output. Okay, so that's kind of similar, but it's less clutter and it's easier to read. And going forward is what I'm going to be using. So here's an example of a simple state transition. So we're in state A, no outputs are being asserted, so we assume they're all 0. Then while we're in state A, we look at Z, right? So there's a whole clock cycle here. And if it's a 1, we go to state C, no change in the outputs. And if it's a 0, the next state will be B. And then when we get to that next state, the output Y will go high. Okay, so if you're in state A and Z equals 0, don't think that Y goes to a 1. It doesn't. Not for another clock cycle. All right? Because you can't change state for a whole clock cycle. I hope this is making sense. No one's saying anything, so I assume this is all perfectly clear. Because it wasn't when I looked at it, believe me. So if you're finding this easy, then, well, that's not fair. All right. Example number 2. This is what I was inferring just now. Ultimately, these decision boxes have to lead to another state. Okay. But we can chain them together. And this is how we test two variables at once. So let's look at this one. If you're in state A, you look at variable P, and if it's a 0 and Q is a 1, all right, both together, so you're in A, P is 0, Q is 1, then the next state will be Y. Sorry, C, talking rubbish. For all the other conditions, we go to B. Okay, so if it's 0 and 0, so P is 0 and Q is 0, or P is 1 and Q is 0. Now, what happens if P is 1 and Q is 1? We don't care, because P only has to be 1 to go to B. So, in other words, that's a very concise way. We don't have to list all the combinations here. All right? So you're in A. If P is 0 and Q is 1, we go to C. And for all the others, we go to B. All right? Which is kind of how you'd write it in VHDL, or if it's a C program in C anyway. All right? You wouldn't exhaustively list all the combinations of the inputs. You think, well, for only a couple which take you in a different place, you test those and then do an else for everything else, which is what this is kind of doing. So this is kind of why it's more compact. Yeah. So there we go. So A, you're in state A, P is 0, Q is a 1. The next state is C, and then on the next clock edge, the state will become C, and the output Y will be a 1. Otherwise, the output Y is a 0. And again, we're not cluttering up the diagram, writing that everywhere. We're just assuming it. Right. And again, if you want inverted logic, you'd write Y bar equals 1. Right. Okay, so P and Q are still associated with state A. They're part of it. So inside the VHDL, when you're looking, you find you're in state A, you'll have if statements, for example, as part of that. Yeah, they're not separate. And lots of implied zeros everywhere. Okay, good. So that's decision boxes covered pretty much. We have a question. Do state blocks have to have outputs? If nothing is written in them, we assume the outputs are 0. So no, they don't at all. As for latching, let's look at that next week, if you don't mind. So there are special types of outputs where you set it, and then unless another state changes it, it stays where it is. I'm not doing that this week. So for this week, right, it's a different symbol as well. For this week, if a box has nothing in it, then the synchronous outputs are just 0. So you don't have to write anything in it. But implied is yes, there are outputs. The outputs never sort of vanish. You just don't have to refer to them. You don't have to write them all over your diagram. I hope that answers your question. Is that all right? Does that make sense? So what I'm saying is that Y is an output all the time. Yeah, but unless you're setting it to 1, you don't have to say anything about it. You don't have to write it in a box. Okay, good. You understood it. Good question. Any other questions while we're here? Are we all right? Excellent. We carry on moving through this fast. Yeah, so there's the dotted line again. That's kind of reinforcing that these are all associated together. Right? They're all part of the same little cluster of code. That's all state A. Good, excellent. Moving on. Now, Mealy outputs. Mealy outputs, if you remember, can change with input signals. So they're a function of the current state and the inputs. So in this diagram, the input is a Z. So we're in state A. And if you're in state A and Z gets set to 1, start engine will become 1 immediately. All right, you don't wait for the next state. And if you remember, sometimes we convert more to Mealy to trim off a few states sometimes, if we're lucky. Right, you can, and sometimes you'll find when you're writing your state machine in VHDL, yeah, good comment. It comes out naturally that way anyway, particularly if they're latching outputs, which we'll talk about. So Mealy engines are, or Mealy machines, sorry, are handled like this. So as I said, so in other words, this start engine, this condition box and state A are still all part of the same thing. Yeah, they're all associated together. So you'll say, well, am I in state A? Yes. Okay, look at Z. If Z's a 1, then you'll just start set engine to 1 straight away in that bit of code. If Z's a 0, we will synchronously go to state B. So the output Y is a more output, and the start engine is a Mealy output. No reason why you can't have both. So what sort of machine is it? Well, I suppose it's a Mealy machine because they're the only ones to have those types of outputs. Right, okay. Good comment from someone saying, that seems very easy and lazy, I like it. Yeah, me too. I agree. Right then. I see my audio, it warned me about my audio dropping out then. I guess that kind of happened. No one said anything, but all right. Now, this is another of these ways where we save ourselves on a lot of pencil lead, basically. Counters, things that just burn loads of states. Not necessarily good designs, actually, but we think of things like this. And I want to get to that in a minute. What we're doing here is we're modeling what we want to implement. And we're doing it with state machines, which isn't, although it sounds like I'm a complete state machine convert, if you like, it's not like that, actually. They are great for working out what it is you want to do and all the timing. When it comes to actual synthesis, you may do things differently, right? And here's an example of that. So if I want to just have 256 states where we just go 0, 1, 2, 3, 4, 5, 6 and count up to 256, 255, a bit like the PWM today, maybe. Yeah, slight nudge and a wink. Then, we start in state 0, we go to state 1, we go to state 2, we go to state 3, yeah, and that keeps going until we get to state 255. And when we get to the 256th state, all right, remember, it only changes once every clock cycle. So this is a counter, yeah, where the state is a kind of internal count. Then I've got a synchronous reset equals 1, so a little pulse comes out at the end. And then I look at the input RCY, which is kind of abbreviation for recycle. And if that's a 1, we go back to the beginning and start again. Otherwise, we stick in state 255. So I don't have to draw 256 circles in a big circle. Yeah? And I'm rather glad I don't, because it gets very tedious, as you can see. So that broken line you see there, that one, right? That's just implied there's a whole ton of them in between, right, in increasing order. So S0, S255, it's saying there's an S1, an S2, an S3, and an S4. All right. I hope that's clear. So when you're doing delays, counters, you don't have to draw every state. All right, and if RCY equals 1, then every 256 states, you'll get a pulse from the reset signal. Right? So we're kind of modeling those sorts of things. Now, you could go off and build that, but I can tell you now, it'll use at least 8 D-type flip-flops, right? And you can do it in less. But that's because you have a repertoire of tricks, ways of doing this. All right. Yeah, because you can see you need an 8-bit number to actually store the state. Well, as I said, there might be other ways, cheaper ways of doing things. Right, okay. Next slide then. Now it gets a bit more complicated. So where are we at in time? I don't want to keep you too long. These webinars are short and to the point, I hope. Okay, 17:25. All right, that's only 20 minutes in. Good. I've actually written an example. I hope it works if I just... it doesn't. If I come out of there and switch to my virtual machine, should get Quartus on the screen. Can everyone see Quartus on the screen? Or I guess you can. All right. This is where it may take a bit longer. Okay, linked state machines. What do I mean by that? Well, if we try to do everything, if you tried to build a whole microprocessor in one state machine, you'd probably fail. It would become a tangled mess. And you'd be also reinventing things like counters when they already exist, like memories, like registers, like arithmetic logic units, adders, multiplexers. Yeah, recognize some of those? We've been building those in term 1. PWM units, those sorts of things. All those sorts of things you can go and model and design, and then you can go in and tune it up and hone it down and use, sort of best practice and what have you. So for counters, for example, you might use a little bit of cascading to keep the number of gates down at risk of adding propagation delay, but there's always a balance. Yeah, you might optimize a design rather than just build a massive great state machine to do it. All right, and that's kind of the example I'm going to use. So here's my problem statement that I decided to solve because it's nice and simple. So there's a single button, X, right? When you press it, it's a 1. When you release it, it's a 0. So I want to make sure that when someone presses it, it's not just a spurious thing. They actually hold it down. I want a quarter of a second, and I'm running at 1024 hertz. Right, that's my clock. So what I want to do is wait for the button to be pressed. When it does, I'm going to count 256 clock cycles, and if they keep the button held down the whole time, that registers as a hit, and the output Y goes to 1. If they let go before that count finishes, no, it's not a hit. Okay, and of course you could make this quite nice. I mean, if you want to do short press, long press for different types of function, for example, then this is the kind of thing you can do. All right, so there are kind of 2 parts to this. There's the sort of logic of the problem, and then there's a timer somewhere involved, which is going to be hooked in, as you can probably guess. All right, so I'll give you a sneak peek now of my solution. Here it is. I've got a counter over here, right, which I've designed so that I can reuse it. All right, it's got a clock input, a start input, and a reset input, and a ready output. Now, I could make it a lot more generic than this, but I want to keep it simple for the point of the lecture. Here, I've got the control, the state machine, that is bespoke for my particular application. It's not a general purpose part. So this is often known as control logic. And this would be part of what's called a data path. All right. So I'm going to look at both. I'm going to look at this one, which is the counter. Now, if I was really sensible, I'd have dived into the library and pulled out a counter that Altera provide, because they're going to do it very well. They know a lot about these things, right? They're experts in their area, and they're likely to use less gates and maybe do it with less propagation delay. Whereas they're not going to solve my problems for me, so I'm going to have to do that bit myself, and that's this control logic here. And notice that they're hooked up. I've got outputs driving the counter to start it and reset it. They share a clock, but the counter output also comes back into my control logic. Okay, so there's a kind of loop, and that's where this gets interesting. So let's talk about that, and you'll see how it all works. So this is all about partitioning problems, breaking them into smaller bits. So not just combinational logic now, but sequential logic as well. And then, because smaller components are easier to test, we can often simulate them, write test benches, those sorts of things, maybe signal tap them. And then we have a chance that when we hook these things together, it's all going to work. Build a massive system, you're going to really struggle to get it to work. If state machine gets too big, you probably need to partition it, which is its own subject, believe it or not. People spend their lives looking at that problem. Right, so the first component I've looked at I thought in my mind, well, I want to time how long this button's pressed for. So I think I need a timer, and I've gone off and designed one that I could probably reuse. And I've used a state machine at this point. Now, as I said earlier, in the final design, I might go revisit this and try and use less flip-flops, less registers, less gates. But for the purpose of modeling, purpose of testing my ideas, getting my logic right, getting my timing right, this is good. All right, so we're going to write a state machine for the timer. So we have this initial state idle. If the start input is low, we stay in the idle state. So that's the kind of loop back. If the start is a 1, we go to state 0. And then that just trundles on off up to state 255. Now I could have added another conditional block in to always go back to idle with a reset, but too much detail. Right, so let's just keep it as simple as that. In idle mode, we're waiting. When we get a start input, the next state will be state 0, and then it'll be 1, then 2, then 3, then 4, up to 255. So 256 states. When we get to state 255, well, the output ready goes high. Now that means that the output ready in these was low. All right, that's that implied output again. But you'll see this is not very cluttered. It's very easy to read. And note the break in the line here, saying that there are intermediate states, beg your pardon. When we get to the last state, if the reset signal is low, we stay there and wait. And if the reset signal is high, we go back to idle and wait for another start bit. So something is providing the start to get it going, and something is providing this synchronous reset input to put it back into the idle state. Okay? You may not like that design, you might want to do it differently, that's okay. So we see 256 states. That sounds like an 8-bit counter to me. So further down the line, I'd be thinking about, maybe not use this. Actually, I'd probably think a bit more cleverly about how to do it. But it models what we want. And that's fine for simulation and testing. Okay, so 2 inputs, 1 output. The start and the reset are synchronous inputs. The ready signal is a synchronous output. So this is a Moore machine. No Mealy outputs here. Okay, so that's my timer. Let's now look at how this fits into the problem that I'm trying to solve. We start in the reset state. So I've called that idle as well. Now remember, this is a completely different component. These are not the same state machine. The timer is this little block over here. 2 inputs, reset and start, output, the ready output. Did I call it ready? No, I called it, yes, ready, yeah. Single output ready. So put that to one side over here, and I can call my states whatever I like, and I've only got 4. So idle state, the output reset is high, and that is hooked up to this timer. So that's telling this timer to go back to its initial state. That's good. We need that. I've not shown asynchronous resets on this. They would be there. That would make the design slightly more complex, but in a way, we don't even need it on here. We just reset everything. So when the X button is not being pressed, so no one's pressing the button at the moment, the timer's reset, it's not doing anything, it's not counting, and I'm not going anywhere in this state machine either. Now, somebody comes along and presses the button X and sets it to 1. On the next state, ST, the start output goes high, and by implication, the reset output goes low. All right. And that will set the start input high on the timer to start the timer off. So reset's low, start is high, and off it goes. Next state is called HD for hold. And there are no outputs there. So start and reset are both back to 0. So we only pulse start high. We only pulse, well, we kept reset high until we went. Okay, so start is a single clock cycle wide. And that's enough to start the timer off. So we're in hold. If the user holds the button down in HD, that's what we want. But the timer is not ready, we stay in this state and hold. So the user is holding the button down. HD, hold. Right. If the user lets go of the button X before the timer finishes, that's this diamond here. So we're back to the idle mode. Okay, and we're staying there. If the user holds the button and the timer hits the 256 state, ready will go high, and that forms this input here. So if you're holding the button down and ready is not high, time hasn't elapsed, but they've still got their finger on the button, we just stay in this state. But if the button's held down and the timer goes off, we go to the DT state and set Y to 1. And that's detected our condition. Now that's not a complete system, because how do we ever get back to here? Well, presumably more stuff happens after this. So we're providing synchronous inputs to this, and we're getting synchronous outputs, and we're using them back in our main state machine. So this is the control, all right? This is the bespoke bit that solves our problem, using and switching on and off and communicating with standard components. Now, if you extend this idea just a little bit, and you think of registers in a CPU, you think of adders that could maybe add 2 registers together, or copy a value from one to the other, or maybe copy something into RAM, you see that we are beginning to see the innards of a microprocessor. All right, and the instruction decoding process will be one of these. Yeah, switch that signal on, switch that one off. Yeah, for different components. All right, and all those components are typically hooked up on a bus. Yeah, so you can see that maybe a microprocessor is not as scary and mystical as you might think. Okay, so that's the simplest example I could come up with in an afternoon anyway, and code up. And I'll show you the code in a minute. Okay, let's do that. So I need to come out of full screen view. Oh, has anyone got any questions? I'm happy to go through any of that. I'm also conscious of time. It's 20 to 6 and it's late. Is that all right? Everyone clear? I mean, as a student, I was never taught this, so I often thought, I wonder how that works. Well, I had to go and find out myself. Okay, now that's my drawings. The state machine. Right, let's start with the timer. Now, I'm going to upload this VHDL onto the module site in a minute. We've got this top level schematic here. I've done this very quickly, so I hope there are no mistakes. So there we see the control, there we see this counter, these are the signals that are sort of routed around. Okay, so let's have a look at the counter. So we edit a time file. Now the zoom doesn't work on GoToWebinar, does it? Okay, I need to make the font bigger. Excuse me a second. Now I try and do that. Customize, probably. Text editor. Customize. No, that's the toolbar. I don't want to do that. What is it? Options? Fonts. Yeah. That was the wrong one. Oh, crikey. I did this the other day. I don't know if anybody else knows how to do this. Put that back to 8. I want to change the editor font. Because you're going to struggle to see this on a remote connection. There must be a way to do it, General. There's fonts again. Text editor fonts. There we go. 12. That's a bit quirky, isn't it? That's better. Crank it up a little bit, maybe. You'd think I'd have done this before I did the webinar. Oh. Okay, so flick back to the timer. There's the state machine. And this kind of resembles its entity, yeah? 2 inputs and an output. And a clock input, not shown. So we've got a clock input, a start to start the thing, a reset to put it back in state 0. We've got an output called ready. Right? So it's important to get your entity sorted out first. And that's really critical. Now I've got an architecture that models this. Again, it probably isn't my final one, because it's not going to be that efficient, and I can show you that. It uses quite a lot of flip-flops. Right, and we can move back and forth now between these. So we've got the idle state, and then we've got 256 states here. Don't want to switch statement with all of those. So I've got 257 states, so that is not going to play nicely. That's one more than I wanted, yeah? Because that now means I need 9 bits. Okay, so I represent my state as an integer because that's just a whole number. I can do all sorts of things with that. I'm never going to output it. It's an internal number. I could remove reset from the process block here because I dropped the asynchronous reset, so I don't actually need that. So clock would be fine. So if the clock rises, and I've initialized my state to 0 because again I dropped my asynchronous reset, which is naughty, but there you are. Keep it clear. So if state is 0, what do? Well, we look at start. If it's 1, the next state is S0, otherwise we stay where we are. So if start is 1, then we set state to 1, otherwise do nothing. So that's if state is 0, else if state is less than 256, remember state's an integer, so I can do that, then we just increment state. That's all this business. 0, 1, 2, 3, 4, 5. Okay, and then I've stuck to the diagram, yeah. Otherwise, if state equals 256, is that the right number? Yeah. If the resets are 1, go back to 0, otherwise stay where you are, do nothing. And if it's some other wild and crazy value, set it to 0. So this is just there as a defense in case something goes really wrong. So yeah, we're in here. These numbers are actually one different from in the machine. Right. Because actually that's state 0, that's state 1, and that's state 256. Maybe I'll change the diagram. All right. So that's it for the state transition. And notice I've put all of that in its own process block. Now, as I said, I'm encoding my state with an integer. I'm throwing implementation to the wind and saying to Quartus, get on with it, and it does a good job. But of course, it can't read my mind. There's only so much it can do to optimize this. Second parallel or concurrent process block is here, where it just looks at a change in state. So when state equals 255, I think that's a bug. That should say 256. Yeah, that should say 256. That's the last one. Well, the output gets set to a 1. And then otherwise, the output is set to a 0. Okay, so that's it. That's it for the outputs. All right, so the ready output only gets set here. And that kind of works with VHDL because it's very similar. Yeah, if state is 256, ready is a 1. Otherwise, it's a 0. Very nice. And that's it. That's my counter. So that's that one built. And by the way, I've tested this all. So next up is this bit, the control. All right, so we've got 1, 2, 3, 4 states here called idle, ST, HD, and DT. 1, 2 inputs, and these 2 outputs. Oh, 3 outputs. We've got Y as well. Mustn't forget that. Okay, let's look at that one. And I say I'll give you this to muse over. I'll just do a couple tests tonight before I upload it, because I don't want to upload something that I've now broken. Control for button. So there we go. We've got the clock in, obviously, the X, which is the button you're pressing. When the timer's ready, we get a feedback signal back in. So that's that one there. The outputs are to reset the timer, start the timer, and of course Y itself, which goes to 1 if we solve the problem. Okay, good. So I've used this nice little thing with this new state type is idle ST I make my state a type, that type, because I don't need to add numbers to this. I don't need to do any arithmetic. It'd be a lot of work to add 1 to idle to get ST. You can do it, but not today. Right, so again, we're only interested in the clock here because I've dropped the asynchronous reset. So if the clock's rising, then we use this nice case statement. Case state. So when idle, if X is 1, state goes to ST, otherwise it stays at idle, which is what this says. I didn't really have to do this bit, the else, but why not? It's clear. It explains what's going on a bit more clearly. When you're in the ST state, then you just advance to the next one, HD. That's what happens here. There, then to there. No inputs. When you're in HD, well, if the button's released, state goes back to idle. Otherwise, see if the timer is ready, and if so, go to DT. So that's this little block here. So yeah, if X is 0, we go back to reset. Otherwise, check to see if timer's ready. It means X is still held down. And the only thing that will make us change state then will be if the timer is ready and the button's still pressed down, in which case we go to DT. And that's captured in that little bit of VHDL there. And I haven't gone any further, so in DT I just stay where I am. Question coming in. Okay, it's interesting you asked that. In VHDL, is there any point in reducing the amount of states if integers are stored as a 32-bit number anyway? Aren't you using the same amount of D-type flip-flops? Right. Because I've used an integer for my state, I've only got 4 states. It should be able to work that out and encode them as a 4-bit number. How can I find out? I mean, certainly what I can do, if I make control button my top level entity a minute and build it. What you can do on the integer is set a range from 0 to from one to the other. But because I've used an enumerated type, it doesn't matter. I think do you mean for the counter? Maybe you mean for the counter. That would make more sense, actually. So yeah, this one would seem worrying. It won't use 32 bits necessarily. Right. I could have put a range on this so that I cap it from 0, and I'd have to try it to see it would help. They don't actually say how many bits an integer is, by the way. Everyone kind of knows, but okay. So the control logic. Oh, hello, I've got an error now. Oh, it's a fitter error. Does not support the device. Oh, drop my network connection. That's all that is. Hang on a second. Let's connect back to the A. It's complaining it can't find the license. Oh, good. Hang on. License setup. I'm connected to the university network, so that should be fine. There it goes. It is fine. Although it's very slow. I'll try that again then. I want to find out how many flip-flops I'm using. So the control one, not many, is the answer. For the counter, that's more interesting. I've got to remember the syntax a minute for the range of an integer, but you can restrict it. But actually, there are better ways of doing this, all right, which wouldn't use a state machine in this way. Here we go. This seems to be working. So for the control, it looks like I've used 4 registers. That's 4 flip-flops. No big deal. For the counter, probably a bit more embarrassing. Oh, it's going off and doing things. Let's just stop it a minute. So the counter is a top-level entity. If I build that one, a lot more. It's saying 32, yeah. So I'm going to try and remember the syntax. I wrote it in my summary thing. Integer range. There we go. Range 1 to 31. Okay, that's it. Um, 0 to 256. So what have I got at the moment? I've got 32 registers. Yeah, because it doesn't know how many I'm going to use. Build it. Let's see if that's helped. Did I save it? Don't know. What's the time? Ooh, heck, running out of time here. Yeah, registers down to 9 now, which is what I'd expect. So yes is the answer. I'm glad you asked that. I have done this before. I think I did it in one of the labs. I don't know if you've done that lab. So yes, by restricting this integer range, I've put a cap on it. And so that's telling the compiler and whatever the tools are called, that you don't need to have all 32 bits. Because the else says, well, it could be any other value, right? Even though there's no way of getting to that value. So yeah, it isn't a mind reader. So the more you steer it, the better. So obviously it'd be nice to get down to 255. That would drop it again. Yeah, it's now down to nine flip flops. So that's quite a saving, but it's still quite a fair bit. Okay, top level BDF, top level entity. I'm short of time now. I was going to demonstrate the timer separately, and then this one. I've done some little vector waveform files because they're nice and visual. Maybe I'll do that as a video to complement this, because that would be good. Okay, so as you can see, the partitioning is helpful. It means I can go off and test this. I can go off and optimize this, and I can, as long as I've got an established interface and I know the timing of it, then this logic can then be developed very efficiently, very clean, separate from each other. Because this is reusable, this probably is not. All right, this is very specific. And I'd like you to, well, it's up to Phil, but as the module leader, I would, and I'm involved with the assessment of Phil's coursework, I would encourage you to try and think like that. Try and, for example, take the pulse width modulator and build it on its own and test it on its own. Right, and you can simulate it before you actually synthesize it and then signal tap. Right. So try and do that. Try and break things down a little bit. I said to quite a few people today, actually, when you build your components, you should, I didn't hear, I know, but you should really put on asynchronous reset so that when you power on, everything is put into a safe state. That means there's 0 volts on the H bridges so the motors don't suddenly leap into life. All right? So you don't have, on power on, you don't have robots jumping off the desk. Okay, so where I'm taking this, not too much further now, because I've only got every alternate week and Phil's got his slots as well. But I do want to go a little bit more into this linked state machine idea, this data path and control partitioning. And we can look at the very essence of a simple microcontroller. And the other thing I would like to just touch on briefly as well, as an example, is the VHDL for some digital interfacing, some serial interfacing, which again is using this pattern, this separation of a controller and some standard components, maybe on a bus. So there we go. That's it for this week. 3 minutes before the hour. Not bad timing. Thanks for the questions you asked. That was really helpful and brought up a few things I forgot to mention. Yeah. So if you've got any more questions, I'll leave the session open. I'll mute the microphone now for 5 minutes, and I'll leave it open for you to type in your questions, and I'll come back on in 5 minutes and answer them if there are any. Otherwise, have a good evening, and see you